Welcome, this is Mr. Dahlstrom going over some of the pre-AP Physics Chapter 7 conceptual book homework problems. In class, as seen on Schoology, there were 15 problems that were assigned. We're going to be going over 6 of them. And so how we did this in class is that if you have a piece of paper, the first 6 is what we did together, and then after that are the ones in chronological order. If you've already started, that's fine. If you've already gotten past these, I just ask that you look back at these and make sure that you have, at least that your answers are correct or that you have enough information there. So the problems that we're going to be looking at today in this relatively short video, hopefully, is 60. 60 is the first one. So 60 talks about, says, a system of particles is known to have zero kinetic energy. Now, when people see system of particles, they might be imagining, hundreds or thousands or millions or billions of particles, but in order for you to have particles, you really only need to have 2 particles. So not only for 60, but also for 61 here. So it says that the system of particles is known to have zero kinetic energy. What can you say about the momentum of the system? So here's where, when we see these weird conceptual problems that may be abstract, if you have equations that you can use to represent these, then that's very, very helpful. So it says that the particles have zero kinetic energy, and so if the kinetic energy here equals 0, then that means, so these do have mass, and that in turn means that the velocity is equal to 0 as well. And so they're asking us, what can you say about the momentum of the system? Well, if none of the particles are moving in the system, then you cannot have any kind of velocity. So if that goes to 0, that also goes to 0. If no particles are moving, because kinetic energy is scalar, we can't have positive and negative kinetic energy canceling each other out. So if there's no overall kinetic energy in the system, there's no momentum of the system either. That's 60 right there. The next one is 61. It says a system of particles. Once again, we can simplify this down to only dealing with, let's say, 2 particles. It says that it's a kinetic energy of 10,000 joules. Now, kinetic energy 10,000 joules, but a total momentum of 0. Explain why this is possible. The 10,000 joules is just there to tell you that you have some amount of kinetic energy. So this basically says that you have the particles and they are moving. So let's imagine that we have a canister of 2 particles here, and we're trying to figure out how is it possible that we can have kinetic energy that is not 0, but we can somehow have a momentum, the total momentum that's 0. And so the total momentum is the momentum of the system. Some answers in class were that the mass would be 0, but it's not a particle if it doesn't occupy space and take up any kind of mass. So some of the examples, if we realize here that how we can have this cancel out is that in order for the total momentum here to be 0, we basically have to have one of the momentums be positive and the other momentum be negative. And how can we have that? We can't have positive or negative mass, so the conclusion is that we can have positive and negative velocity relative to each other. So one object can be moving up, and then the other object, let's say, is moving down. It really can be any orientation here, where this would, first mass here going up would have a positive velocity, causing this to occur, and then the second one would have a negative velocity, causing there to be negative momentum. We're not even talking about the collision, so this is going in order of the book. We're just at momentum, we're right at the beginning. We're not even talking about collisions, we're just talking about 2 particles that are moving, and if they're moving in opposite directions, the overall momentum is 0. So that's how particles can be moving, but also have momentum. As opposed to number 60, if they're not moving, you can't have momentum, but if you don't have momentum, you can still be moving, because we're counting all the particles together. The next one we looked at skips over here to talking about impulse, and just a reminder, 73 is one you're going to have to do. So we'll just talk about this before we do the one we're talking about, which is 74 and 75. 74 says, how does force differ from impulse? Impulse is both force times time. It's both force times time, and it's mass times change in velocity. So once again, we're here. Impulse, as we said in class, traditionally is written as force times time, but we have to realize the impulse is also equal to change in momentum, and change in momentum is equal to m delta v. So you have 2 parts to that. You have force times time equals m delta v. Impulse can be using these two. Impulse can be using these two. So the difference is that force is just the force applied, where impulse is the force with how long the force is being applied for. So using that idea, 74, is it possible for a small force to deliver a greater impulse than a large force? If people are getting this wrong, usually there's like, okay, small force creates small acceleration, large force is large acceleration, so certainly the large force is going to be a greater impulse. We talked about this in class, and I think there was in the notes as well, even if you weren't in class here, about the difference between different types of propulsion in space. So you have rocket propulsion here, and then you have ion propulsion there. Rocket propulsion, let's say you're just trying to change the momentum here. Okay, they're both trying to change the momentum. In a rocket, you have a relatively large force, but that force is only applied over a short amount of time. Minutes, tens of minutes, 20 minutes. Whereas in ion propulsion, here you have an enormous amount of force at the back. Ion propulsion, you're literally shooting out electrons out the back of that, a lot of electrons, but the force is extremely small, but you can make up for the fact that the force is small by having it run over an extremely large amount of time. So if we understand that if we're trying to change the momentum or impulse here, it's not just based on force, it's based on force and time. So the question here is that, is it possible for a small force to deliver a greater impulse than a large force? Yes. The only way that this would be able to happen is that if our small force was applied over a longer time. This right here would produce a greater change in momentum than what we had originally. The longer the time, it's just saying you're looking at both of the numbers together. It's not just a large force is a greater speed. A large force and a small force can both produce not only the same same change in momentum, but the same impulse, because the times are inversely related to those. So is it possible? Yes, it would just have to be running for more time. Okay, so possible. That builds also into the idea of 75. 75, triple choice. It says, so let me pre-explain the problem here before we read it. 75 is basically you have one school bus and you're looking at two different scenarios. In the first scenario, they say that the school bus is driving along at some velocity, and they say that they're stopping at a stop sign, and the bus driver lightly presses on the brake, and so it takes a very long time to slow down. You're then comparing that to the second scenario where, once again, same initial velocity, same mass, same final velocity, but in this case, the bus driver slams on the brake, coming to a very, very fast halt. And so once again, we'll just read this to compare. It says, as a school bus approaches a stop sign, the driver applies the brakes and brings the bus to a slow, gradual stop. So what would that look like? You would have a small force here, but the time would take a long time. There's the slow, gradual. And then they'd said instead, if the driver had instead stomped on the brakes and brought the bus to a sudden stop, let's look at this. That would mean that would be a large force over a short time. Okay? They're asking, if the driver had instead stomped on the brakes and brought the bus to a sudden stop, don't worry about the magnitude, would the impulse be greater than, less than, or equal to the impulse with the gradual stop? So they're saying by stomping on it, would the impulse be greater, lesser than, or equal to this? Now, you may argue, like, well, I don't know what the force is, and I don't really know what the time is, but this answer, we need to remember that impulse is not just force times time. Yes, this may be a small force that we may not even know what this is, or this is, or this is, or this is, but remember that impulse also equals change in momentum, which is mass times change in velocity. Let's take a look. Both these school buses have the same exact mass. Okay? And they both are going from the same speed to rest. It's the same scenario. So they both have the same delta V. And it's interesting about this part of measuring impulse is that there's no mention about how much force it takes, no mention about how much time. Just the fact that you have two exactly same school buses going the exact same speed and ending at the exact same speed at rest means that this momentum is equal to this momentum. So that change of momentum is equal to that change of momentum, which means that both of the impulses are equal to each other. So we didn't really need to necessarily look at force times time. We could have just realized in the setup, it's the same bus with the same mass going the same speed and coming to a stop. Doesn't matter how long it takes, doesn't matter how short it takes, doesn't matter how much force there is. This right here, to answer the question, this right here is enough to say that those two are equal to each other. Okay. So the impulse would be equal. Why? Because the change of momentum is equal, and those two are the same. Impulse is change of momentum is impulse. Let's now move on to some conceptual questions relating to conservation of momentum. I'll set this up. What 89 is saying here says, give an example of a situation where momentum is conserved but velocity is not. Every situation, momentum is conserved. Momentum is always conserved for all collisions, interactions, but velocity is not always. And in the class, I showed carts moving back and forth, and it's not easy to do this. But earlier, when we were doing notes, I talked about a cue ball and a one ball. So let's think about pool balls. Pool balls, the mass of the balls, we're assuming at least here the mass of the balls are the same. So although the momentum may change for the cue ball from here to there, it is losing momentum because it loses velocity. It is being exactly gained by the one ball by speeding up here. So momentum is conserved. The total momentum we have over here is all in the cue ball, and all the total momentum we have over here is now in the one ball. Momentum is conserved. However, the velocity is not conserved here because, well, we can see here that it's clearly moving here, and here it's at rest. So the cue ball stopped moving, velocity not conserved. Same thing with the one ball. Initially it wasn't moving, now it is moving. So once again we have a gain in velocity, but the velocity is not conserved for the individual ball because it's gaining that. So just the same way that the individual momentum is not conserved, the total momentum, so how much this loses, how much this is gained, but the individual velocity for the particles or for the ball is not moving. You could also think of an example where we showed in class if you have a rifle and you have a bullet here, the velocity for both of these equals 0. Let's say for the rifle is 0, the velocity for the bullet is 0. And then once it's fired, we have the rifle, which is now moving backwards with some negative velocity, and the bullet is moving forward with some positive velocity. There's another situation where momentum is conserved. It'll end up, if we multiply the masses, the total momentum on this side will have to be 0, but the velocities are not conserved. So there's a lot of examples where momentum is, well, all of them are conserved with momentum, but velocity is not conserved for 89. 90, I'm going to please have you just kind of take a side off a little bit of history here. Explain how a rocket functions in space, even though there's no matter for it to exhaust the gases to push against. So I'm going to go over here. This is interesting. Please pay attention. Please watch the whole little part here. So there was a belief for a very long time leading up to the 1920s and even further. So airplane, 1903 or around the early 1900s, the Wright brothers airplane, and there was a claim. There was a person named Robert Goddard and other people that were trying to do experiments with rockets, and there was a claim that space flight was impossible. What was the claim? Is the claim that up to that point it was a consensus, it was a settled science, especially among there's a lot of articles in the New York Times where they basically made fun of Robert Goddard and said, "Ha, you don't know Newton's three laws. You don't even know what's being taught in high school physics." And so everybody said, there's no way. Why? Because they said, if there's nothing for the rocket to push against, there's nothing that it can go. So here's an analogy for sort of their misunderstanding. So if we had a person, if you were standing on the floor and you wanted to jump up, you have to push your legs into the floor. and then Newton's third law says it will push you up there, so you can jump. It's successful. However, if you were to suspend yourself, let's say from just from the ceiling with some rods or rings or something like that, and you were to take your legs and try to take them and then like thrust your legs downward here, there's nothing to push off against, so you're not going to move upwards at all. You could flail as much as you want. You're not going to be moving at all because of your legs. So they said because there's nothing that this person is pushing against, they're not going to be going up. Same thing. They said, okay, if there's no ground or there's no air for the rocket thrust to push against, it's not going to go anywhere. Robert Goddard had an idea. They basically tried to discredit him, and so he set up an experiment where he tried to show, okay, you guys are wrong. You don't understand Newton's three laws. You don't understand conservation of momentum, and Robert Goddard is you might eventually know that Robert Goddard is an important person in rocketry because eventually NASA named the Robert Goddard Space Flight Center after him, so he might be a little bit influential. But what he set up is he set up this case here where he pulled a perfect vacuum. He was trying to mimic what it was like in space. He placed a gun and he placed a bullet inside the vacuum. And the understanding at the time is that the reason that the gun recoiled is that because there's air that is inside the barrel, when the bullet was being pushed against the air, the bullet was also in contact with the rifle, and that's what pushed it back. So the fact that the bullet was sort of part of the rifle, and when the bullet traveled down, just like the people's legs traveled down, it was pushing against the air, and the air pushed back on the rifle, and that's why it occurred. That's not how it actually works. So when he fired it in there, unspectacularly, or I guess spectacular to everybody else, the bullet fired out, and the gun recoiled, even though there was nothing to push against. And the explanation that was given here is that you're not understanding. Here we have it's a conservation of momentum. Here you have a small mass moving at a very large velocity, but because, in this case it's a recoil, but because momentum is conserved here, we have a much bigger mass that is going to have a velocity in the opposite direction. We actually derived Newton's third law from this. If you do this there, if you do this there, you get ma equals ma, which basically says that the force on one is equal to the force on other. And so he was able to show that this is reality. It wasn't actually until after his death that he started to actually get credit for that, unfortunately, that he was kind of a pioneer. Not only, just a little aside here, if we compared the vacuum of space versus atmospheric pressure in thrust, the leading people at the time, they're saying, okay, there's nothing to push off against. So they were saying, even if you somehow could have thrust, still the belief was that if you fire a rocket or the rocket exhaust into the atmosphere or with pressure around, you're going to get a greater push off. When in reality, that's not the case. The reason that that's not the case is that the fuel that's inside wants to go out. And it wants to go out, and it basically stays in a straight line. The reason it stays in a straight line is that you have so much pressure from the outside atmosphere that is reducing that. I mean, the faster the thrust goes out, the faster the rocket's going to go forward. But if it has a hard time even getting out because you have pressure, it's going to result in a slower velocity. However, if you go to a vacuum, once again, you have this fuel that wants to get out. Not only is it being thrust out with pumps or rockets that are reaction there's nothing to stop it. So it actually flames out in a huge sort of manner like this, and you see the thrust. It expands because there's no pressure, there's nothing keeping it in, and it also comes out much faster. So this results in a much higher velocity. So doubly, not only were they incorrect on how rocketry was impossible, but they were also doubly incorrect that a rocket in the atmosphere would actually work better than the vacuum of space. So Robert Goddard, good guy. Look him up. Research. One of the fathers of rocketry. So we go back to the question here. Hopefully you did not just skip past all that because you didn't learn anything if you did that. Explain how a rocket functions in space even though there's no matter for its exhaust gases to push against. It's this right here. It is a recoil. we can say the initial velocity before of both of them is 0. So in order for the bullet to be fired this way, there's momentum that is given here. That means that there equally needs to be some amount of momentum on the other side. This momentum is positive, this momentum is negative, and those end up canceling each other out. Not that they're not moving, but the total momentum afterward is 0, just as it was when they were together not moving. So conservation of momentum, one thing is thrust one way, the other thing is automatically going to move it. There doesn't need to be anything there. The last one we're going to look at here is number 103, that's talking about collisions. And it says, can two objects excuse me, on a horizontal frictionless surface have a collision in which all the initial kinetic energy of the system is lost? Explain why or not, and all those. So let's first look at an example here of two objects that would have some amount of kinetic energy. So remember, kinetic energy is a scalar. There is no direction. So here we have some kinetic energy. Here we have some kinetic energy. But in order for the two objects to not have any kinetic energy after, they would have to collide in such a way that even though their masses are combining here, the velocity here would have to be 0, because it's 1/2 m, I guess both of them, m1 plus mvf squared. So in order for this kinetic energy to equal 0, be dissipated, we would have to have an inelastic collision, not just an ordinary inelastic collision, but an inelastic collision where the two objects come together and they stop. Because you can't have some where the ones keep moving, or things like this where they collide and they keep moving, but it has to be something where they collide and they stop. So inelastic where they stop. So that's what we did in class. The remainder of the problems are listed up on Schoology. And so either upon your return, or actually I think I have a place that you can turn in the problems, or I will shortly. If you can submit those, that'd be beneficial. So thank you very much. Try to shut in this video. Appreciate you watching.